My name is Shreya, and I'm going to be presenting my Physics 2212 Lab 2, which is Charge Tape Revisited. Essentially, in this lab, we're going to be kind of looking at the same concepts and experiment as Lab 1 with the charge tapes, but instead of looking at them as point charges, we're going to be looking at them as uniformly distributed lines of charge, essentially. So, lab setup is basically the same. We created two charge tapes, and we have one that's kind of on the bottom that has the same charge as that top one right there. And we lift that second one until there's a displacement between the two charges, and it kind of the first charge kind of floats there and stays there for a while. And that kind of indicates that there is an equilibrium of forces going on. So there's a force of gravity, and then also the upwards force of um, the charge of the bottom tape, because they're both positively charged, so they repel each other. And so some observations that I found was that obviously the tapes were kind of repelling, but when we kind of touched our finger to it, it would attract to our finger because our fingers are kind of acting as dipoles. And then we also observed and measured that distance between tape A and tape B, which is helpful for the simulation that we've created for Lab 2. So some important equations that we used in this lab and also in the previous lab is the electric force formula shown right here. This uses the charges. This is a point charge formula, but uses the charge of the 2 point charges and K, the constant, as well as R, which is like the distance, magnitude of the distance between those two. For the vector form of this, you would just multiply this by the unit vector of R. We also have the electric field formula, which we will use a lot in this lab, and the force of gravity formula. And then here, this new one, this is kind of the continuous charge distribution. It's finding that integral or the sum of, for every like dq um, or dr, we want to find like that electric field and then kind of sum them all up or take the integral for a continuous distribution to find like that net electric field. So in this lab, we want to find the amount of charge on each tape that's required for the top tape to float on top of that bottom one and have like no momentum. So once again, that balance of forces due to the gravity and that electric force as well. So for this, we wrote a program that will allow me to estimate that charge, and I'll put that the net electric field and then gravity. So in the ideal case, the correct charge will allow me to have the same exact force of gravity as well as that electric force. So let's start with kind of looking through my code. At first, I actually just initialized a lot of like the key constants that we need. So obviously gravity and K. And then we also have the mass of one tape. We've calculated this in the previous lab. And then Q, this is kind of what we are trying to play around with and what we're experimenting with. And the value that is the result of this lab at the end of the day. So I actually started off with the value that I found for the tape using calculations in my last lab, lab one, and I went from there. And then I also initialized and defined the E-field method, which given a charged particle in an observed location, it will output the electric field at that location due to the point charge with that simple formula we saw in the previous slide. All right, so now this is kind of the meat of it, but basically, for the code simulation, we have two nested for loops. What this essentially does, right? We already initialize like this FE, which is electric field on the top tape. And these scales are just for the arrows, but what we kind of want to do here, right, is we are essentially going to be playing around with this um, like for every DQ top, like we have a series of points on this top charge tape, and then a series of points on this bottom one. For every top point, we want to kind of iterate through all of the bottom ones and calculate that electric field using that for the formula that I created in the previous slide. And I want to sum up all of those electric fields for each and every DQ top, right? So I do that for every DQ top. I look at every DQ bottom, sum up that electric field, and I equate that. So it creates kind of a series of arrows, essentially. Um, so after that, I kind of print those answers that I get, and I find that net one by summing everything. I find net electric field and force of gravity. So the result of the simulation, this is just showing the electric fields at each DQ or each point that is defined on the two charged lines. And as you can see, like this bottom line was the bottom tape and the red line was the top tape. And this kind of shows like that distribution. And essentially what I did was I kind of played around with this Q value until I found the optimal value of 2.60116 times 10 to the negative 8. And that essentially um, made it so that my magnitude of electric force and magnitude of gravitational force was exactly equal. So concluding questions of this lab, some assumptions, approximations, and idealizations I made was that for any moving object, air resistance did not matter, and I did not account for that or air friction. In the last lab, we assumed that each tape was a point charge, but in this lab, we assumed that each U tape had the same amount of charge and was evenly distributed along the length of that tape. So that's why we use like different points in that iteration aspect of our algorithm there. Thank you so much for watching. And that was lab 2.